Can you see my screen now?
Yes, sir.
Okay, thanks. By the way, I will leave today 30 minutes earlier because I have to see a doctor. So maybe I can take half an hour extra in the next class sometime in the next week. So today I'll leave at 4:30. Anyway, okay, so let me recall what we did in the last class. So in the last class, we introduced matrix norm. So as I mentioned that although space of matrices can be treated as a because it's of dimension, let's say if the space of matrix, if the matrices are of size n cross m, then it is of dimension nm, and this space of matrices can be treated as let's say fnm. So then whatever norms we have defined on or whatever vector norms we have defined on these spaces, they can be used to measure matrices also. That's true. But then because there is a natural multiplication defined on the space of matrices, we can multiply two matrices, and therefore the natural thing is to like, okay, whether we can relate the size of the product to the sizes of the individual matrices. And therefore in order to like take care of that, we define matrix norm. So what is a matrix norm? Matrix norm is any function from the space of matrices to R that satisfy 5 properties. The first 4 properties are the same as of vector norm, and the last property, which is the submultiplicativity, that means norm of AB is less than equal to product of their individual norm. So if any function that satisfy these properties, then it is called a matrix norm. Okay, so we saw we made some observation also. So today we start by giving some examples of matrix norm. Okay, all right, so let us see some examples. So suppose that we have A n cross n matrix over C, and the entries are denoted by Aij. Then as I mentioned that we can treat this space n cross n space of matrices, is a space of n cross n matrices. This we can treat as a Cn square, right? Because it is isomorphic to this space. So every column we can stack up on each other, and then we can treat it as a like Cn square. So therefore, whatever norm we know on this, we can first consider those norms, and then we can say whether we can at least check whether those norms are matrix norm or not. For example, uh, if you define one norm, so what is this one norm? It's a LP, it's a L1 norm, which is defined on Cn square. So how we define on this space of matrices? So it is this function. It's a sum of all the absolute of all the entries of A. The summation is taken over I and J. Okay. Now this is sort of L1 type norm, right? And you can check that this satisfy all the 4 properties of vector norm. Not only that, it also satisfies the submultiplicativity, so that this function becomes a matrix norm. So this is a matrix norm, and you can verify that this is a matrix norm. Not only this, there are other norms also the same way we can define. For example, the 2 norm we can define L2 norm on this space of matrices. And how it is defined? It's defined in the same way. You take the summation, the square of the summation of square of absolute value of each entry of this matrix, and then take their square root. This, if you carefully look at this thing, this summation is also the same thing as you take the trace of A and A star. A star is the complex conjugate transpose of A. So if you take this also, then it is the same thing. So you can verify again using the Cauchy-Schwarz inequality. You can again show that this matrix, this function is a matrix norm. It is clearly a vector norm, It is because it is like in fact it's a L2 norm, but it also satisfies the submultiplicativity, so it becomes matrix norm. So this is also fine. Similarly, you can define infinity norm, right? So what is that? So if you want to define the same way infinity norm or L infinity norm on this space of matrices, so what it would be? It would be max of mod Aij, and this maximum is taken over all entries Ij, all Ij entry of A. Now this, for this norm, this function, you can verify again the same way. You can start by verifying one by one all the properties of a matrix norm. And you will see that this function is a vector norm. It's definitely, it satisfies all the properties of vector norm because it's a L infinity norm only on a space of Cn square. But it doesn't satisfy submultiplicativity, and therefore it is a vector norm, but it is not a matrix norm. So this is a vector norm, but not a matrix norm. So why it is? So for example, if you take this two by two example, let's say you take this example where all the entries are equal to 1, and then look at a square. What would be a square? It is 2, 2, 2. Okay. So if you look at the infinity norm of a square, what it is 2, right? And similarly, if you look at the infinity norm of a, that is 1. So what does it mean? This implies that this is strictly greater than square of infinity norm of a, because this is 2 and this is 1 square, which is equal to 1. So it is definitely greater than 1. And therefore it contradicts one of the observation which we made in the last class, because if this is a matrix norm, then for every matrix A, this inequality should be true, right? This we have seen because of the submultiplicativity, this has to be true, but because of this you can see that this function doesn't define a matrix norm. This is not a matrix norm. But if you slightly change the function here, if I slightly modify, so let me give you this as an exercise. So if I slightly modify here this function, that means I'm defining using the same function but with a slight change. That means the new function is this one. So what is this function? So it is a function from n cross n matrices to R defined by this, where this here A infinity is the same as I have defined here. Okay. Now this function is a matrix norm. So A infinity is this infinity norm is not a matrix norm, but now with this modification, this function here becomes a matrix norm. Okay. So this you can verify. In fact, I can tell you why this is true. Then this function is a matrix norm. All right, so why this is? So let me give you some hint. So the first four properties, they follow because of this thing, that this is a vector norm. So the first four properties of matrix norm, they are quite obvious to check. But the last property, which was not satisfied by this infinity norm here, that you need to check whether that is satisfied or not. Okay. So let us take two matrices A and B and look at the function value of this product. Okay. Suppose that A is denoted by Aij and B is denoted by Bij. Okay. So by definition, what it is? It is just n multiplication of this. All right. But then we know how this infinity norm is defined. It is the maximum over all entries of this product AB. But the ijth, or let's say ikth entry of this product AB, how would it look like? So it would be like j equal to 1 to n. Aij Bjk. Okay, so this is the ikth entry, or you can also write it like, let's say, I can also write it in this way, aik bkj, and this is k equal to 1 to n ij, where ij are the indices which are running over all the entries, right? But then this quantity here, this you can write as this is less than equal to, when you take the modulus inside, then because of the triangle inequality, we lose the equality sign here, so it becomes inequality. So it would be n times max of, so you take this modulus inside, it would be aik bkj, right? And maximum is over all ij, right? But then, you know, this is the same thing, you can also write it in this way. This is less than equal to n. So what I'm doing here, I'm replacing each of these entry here with the infinity norm of, so the each entry here with the infinity norm of a, because infinity norm of a is the max over all such entries. And similarly, I will replace this also with the infinity norm of b. So clearly this is a less than equal to thing. This is less than equal to n, and this would be k equal to 1 to n norm a infinity times norm b infinity. So what it would be? It would be n square a infinity b, which is equal to, oh sorry, this is actually equal, which is equal to n. You can write it in this way. So the first quantity here, the first term, is nothing but this is this one, and this is this one. So clearly this function is satisfying submultiplicativity, and therefore it becomes a matrix norm. Okay, so you can see that the function itself, the infinity norm itself, is not a matrix norm, but with a slight modification, you can make it as a matrix norm. Okay. Okay, so there are several other, so this way you can talk about other norms also, and then you can check whether whatever norm you have defined on Cn, whether they become a matrix norm or not. You can verify them. But there is a, like, associated with each vector norm, there is a natural matrix norm that is induced by the vector norm on uh, on the space of matrices. So what I'm saying is that if suppose you have a like, if suppose you are, let's say you have a, let's say you have a space of matrices over F, where F is either R or C. Okay, then you can take any vector norm on Fn, any vector norm on Fn. Now using this vector norm on Fn, you can define a matrix norm on these, which is induced by this vector norm. So, or once I give you this, then you will see that this also gives you a way to, like, another way to define norms on a given space. So it is another way to define norms. So we have already seen several ways to define vector norms. This in fact gives you a way to define matrix norm on a space of matrices. Okay, so let us first look at, before I define it in this way, let us first look at define this function, and then we'll see whether this function is a matrix norm or not. So suppose that we have an n cross n matrices over here. This is the space of matrices. Now this matrix A, this I can treat as an operator, right? So this I can treat as an operator from Fn to Fn. Right? Now if I take any norm on this, let's say if I take one norm on, let's say let us fix some norm on this Fn, okay, and the same norm I'm using suppose for this also for the codomain. So if I have a vector norm on this, then I can define this function. Uh, so where norm Ax, so this is well defined thing because they belong, Ax and X both belong to Fn. So this is fine. And in fact, if you just restrict yourself to norm1 vector, then instead of supremum, you can talk about maximum. So this is a well-defined function, and then you can give it a name. We'll give it a name, like we'll call it operator norm. But you can check that this function satisfy all the 4 properties. That also we'll see, and therefore we can actually define a matrix norm. But then you can say, okay, why to restrict the same, use the same norm on domain and codomain? Well, you can use different norms also. For example, let's say you can use some alpha norm on the domain and some beta norm on the codomain, and therefore you can do it in this way also. Still, this becomes a matrix norm. This satisfy all the properties of matrix norm, and therefore this becomes a matrix norm. But to keep everything simple, or to keep the notation in a simplified form, we will use the same norm on domain as well as on codomain. All right, so let us define it now precisely. So if we have a matrix, then we can treat this as an operator. Okay, so if let's say if I have a norm, vector norm, in fact, we have a vector norm on Fn. So if suppose this is a vector norm on Fn, then we can define a function. Let us call this function. I'm denoting this function just to differentiate, or just to say that this norm is induced by some vector norm. I'm using this different notation with 3 bar each side. So this notation is to denote the operator norm, which we'll call this as operator norm, but this is a different notation I'm using. So this is for a function from n cross n to R. And how it is defined? It is defined by this rule that if you take any A, matrix A, then send it to this value, max of nth of Ax. X is in Fn, and you can restrict yourself to norm1 vector. So now first thing is that, so this we have defined. I'm not saying that this is a norm. We will prove that this is actually a matrix norm. But so far we have just defined that if we have a matrix A, then we can treat it as an operator. So if we have if we have any vector norm on Fn, then using that vector norm, we can define a function from space of matrices to R in this way. Now the thing is that whether this function is well defined. Yes, this function is well defined. Why? Because norm, since this is a vector norm, and norm is a continuous function. So this is a continuous function, and here we have a compact set, closed and bounded set. So it will attain its supremum. So this max always exists. So this function is a well defined thing. Okay. So this function is well defined, and then we will see that this function is actually gives us a matrix norm. But before that, I will make an observation that can make this observation here. So what is that? So what I'm saying is that although I have just for the definition I have used this set here, I'm only allowing norm1 vectors here. But this max is same as maximum over all non-zero x, and maximum of this ratio norm Ax divided by norm x. These two things are same. Not only this is actually equal to if you take the maximum over a unit ball. So that means you allow vectors which are of length or which are of norm less than equal to 1. So all these three things. So the first thing is what we have used to define this function, but in fact you can show that these two max are also two maximum also same as this one. This I can tell you why this is true. This is a very simple observation. One thing is clear, so let me denote. Let's say this is, let's say 1. This is the second 2, and then this is 3. So I will show first that 1 is equal to 2. Clearly, one thing is clear, that 2 is greater than equal to 1. Why 2 is greater than equal to 1? Because in 2 we have a larger set, and if we take the maximum over a larger set, then obviously it is always greater than equal to. So this is obvious. Now to show that 2 is less than equal to 1, we do the following. So if, let's say, that x is not equal to 0, and then what I will do, I'll set x hat, which is x divided by its norm. So that this x hat becomes a norm 1 vector. Now clearly, if you do this, then this quantity norm of ax, this is always less than equal to 1, because 1 is the maximum over all such overall norm 1 vector. This is less than equal to, right? But then what is this? This is nothing but a x hat is just x divided by norm x less than equal to 1. Or let me just write this equal to this. Okay. So what we have is that we have norm x divided by x is less than equal to 1, and this is true for all x non-zero, because we started with a non-zero vector x. But then if this is true for all non-zero x, then if you take the maximum, that is also the maximum over all such vectors would also be less than equal to 1. So we can say from here that 2 is less than equal to 1. So this way 1 is equal to 2, and similarly you can show that 3 is equal to 1. So this you can take as an exercise. All right, so these three things are equivalent. Now I'll claim that this function, whatever I have defined, this is a matrix now. So you can verify this also. So I'll write this as a result, that the function is here define above. This is a matrix now. This is a matrix now. Now you can verify that. So in order to check whether this is a matrix or matrix norm or not, we have to check the all five conditions. The first four conditions are very straightforward to check. In fact, the non-negativity, that you can verify easily here. So non-negativity, every element here in this so this function is non-negative, so the maximum will also be non-negative. So the non-negativity is clear. Positivity, this maximum is attained. So I mean, this supremum is attained. This is the maximum, so it will be attained at some point, right? So that means norm of ax is 0 if and only if x itself is 0. So the maximum is 0. That means at every point this function is 0. So that means the matrix A itself is 0. So that is also clear, the positivity. Homogeneity is also true because of the fact that this is a vector norm. So if you take and multiply with any alpha, then you can take modulus of alpha outside, and this is the same thing. So homogeneity is also fine. Triangle inequality also follows by using the triangle inequality of the vector norm here. So that is also easy to check. Now the only thing which is important here, or which is different, or which is difficult to check, is the submultiplicativity. So let us check whether this norm satisfies the fifth property, submultiplicativity. So Let us check that. So first thing I'll write here, non-negativity, we have verified quickly, it is fine. Then the positivity, that also you can check easily, that is also fine. Homogeneity, that also you can check, and similarly triangle inequality. So these four properties follows by using the fact that in defining this we have used a vector norm. So this is also fine. Now the only thing is to check this submultiplicativity. Okay. So let us check. Okay, so how to do that? So if in order to check the submultiplicativity, I will look at this product. So by definition, what it is max of x non-zero bx divided by norm x, right? Now, one thing is clear that this maximum is not attained. This we can assume that this maximum here, so in this function, this maximum is not attained for vector x for which bx equal to 0, because if bx equal to 0, then here this function, this is 0, this is 0, this is 0, then that means ab, the product is 0. So what we can say from here, that this maximum is not attained for vectors which are in the null space of B, right? So clearly, without loss of generality, we can assume that this maximum is taken over all x for which bx is not equal to 0. So what I can do here, I can do the following, because this maximum is taken over all vectors x such that bx is not equal to 0. So I can do the following, I can divide with bx. Why this is true? Because so without loss of generality, we can assume that maximum is taken over all x such that bx is not equal to 0. Okay. So we assume that, you can write, we assume that without loss of generality, maximum is taken over all x such that bx is not equal to 0. Right. So in fact, what you can say from here now, since bx is not equal to 0, you can write it in this way also, that x not equal to 0, not so you can write it in this way, maximum over all x such that bx is not equal to 0. So you can write that x is not in the null space of B, and then a bx divided by, right? But then you can do it in this way now. This is less than equal to, you can write y for bx, so it would be y not equal to 0, ay, right? And here also you can with this less than equal to, you can write the following, right? But then what is the first term? First term is nothing but the value of a under this function, and similarly the second term is the value of b under this function. Okay, so this function also satisfies submultiplicativity, and therefore this is a matrix norm, and we call it a matrix norm induced by the given vector norm, or it is also known as operator norm. Okay, so whenever there is you define this kind of function, you don't have to check that whether that function is a matrix norm, because now this result says that all such functions are they define a matrix norm. So if your function is defined in this way, then so once you define your function in this way, then that becomes a matrix norm. You don't have to check separately whether that function is a matrix norm or not. So that you can say because of this result. So all such functions define a matrix norm. So for example, I can give you, now you can give me several examples. So for example, is a matrix norm, and we call this norm as an operator norm. It's a matrix norm, and we call it operator norm. Okay. So let us see some examples here. For example, you can define, if the vector norm you choose on Fn as a L1 norm, then you can define operator 1 norm. Like, what is this? So this notation you can use, or you can define, or this function you can define when you have when you use L1 norm on Fn. Okay. So this is where this norm is L1 norm on Cn, let's say. Similarly, you can define operator 2 norm. So what is this? This is defined the same way. Now, in order to say that this function is a norm, we don't have to check. It is just the way it is defined, it becomes a matrix norm because of the previous result. So this is operator 2 norm, and sorry, where this is a this is L2 norm on Cn. Similarly, you can define infinity norm, infinity operator norm, the same way. You can take any vector norm on Fn, and using that you can define this operator norm. So this norm is induced by the given vector norm, and we are calling this as operator norm. So the first one is operator 1 norm, then you can define operator 2 norm, and this is operator infinity norm. In fact, you can define any operator p norm using the same way, where p is greater than 1, less than infinity. Okay. By the way, I just want to mention one thing here. While giving you examples of matrix norm, yeah, here I said that this is a matrix norm. So this is a matrix norm, but it has a name. It is called Frobenius norm. We call this as a Frobenius norm. Why I'm mentioning this? Because this norm is also one of very useful norms, and in fact, it has several properties. We will see it later on. So I want to give a specific name to this. I mean, it's a standard name. So we'll also call it, instead of this L2 norm, we will use it Frobenius norm to denote this norm. All right. Okay. So now this is fine that we have defined like a class of norms, which is operator norm here. We have defined several norms on space of matrices, but now thing is that how to find. So for example, if we are given a matrix, then how to find its operator norm. Let's say operator 2 norm, like we have defined here. So let us take one example. So the question is to find 2 norm, this operator 2 norm of a diagonal matrix. What would be the 2 norm of the diagonal matrix? Let's say call it D, where the diagonal entries are denoted by D1 to Dn. Okay. So how to find the operator 2 norm? So can you guess something? What would be the operator 2 norm of this diagonal matrix? Can you give me some hints? Or just first guess. We will see how to do that. I'll tell you how to find. But can you guess something? Because this is a particular matrix, it's a diagonal matrix. So just look at this now, this function here. Can you say that this would be the value of, if I take any diagonal matrix D, then the operator 2 norm would be this. Can you guess something here? All right, so how to do that? So let us look at again what is how this is defined to know. It is the maximum for all non-zero x, maximum of this ratio dx divided by. So clearly, as I mentioned earlier also, you can write this maximum as supremum also. It's actually supremum, but since it is attained, so it becomes maximum. Okay. Now we are trying to find maximum of a set. So how to do that? We have to first we need to first find an upper bound, and then we have to show that this is the least upper bound. This is how we find supremum, right? Or in the case when maximum supremum is attained, maximum. We do it in this way. So we at this point we don't know what would be the maximum of this function. So what I will do, I will first find an upper bound, and then I'll show that that upper bound is the least upper bound by showing that this bound is attained. Okay. So what I will do here, so let us take any non-zero x. So first I will find an upper bound. So let's say let us start with the non-zero x, and let us assume that x has this these entries x1, x2, and so on up to xn. So this is our x column vector. Then what would be the 2 norm of dx? So it is by definition, let's say square of 2 norm of dx. What would be this? By definition, it would be di xi, right? Modulus of di xi square I equal to 1 to n, summation I equal to 1 to n, right? But then this is same as di square xi square I equal to 1 to n, right? But then what I can do here? Can you tell me what should I do next? I need to find an upper bound for this.
Take the maximum of all DIs.
Yeah, so if I take the maximum of all di's, so what it would be? So basically this would be less than equal to, if I replace each di here with the max of all di, so it would be max of mod di square, then I can take out I equal to 1 to n, and then summation mod xi square I equal to 1 to n, right? So what I can say from here, that 2 norm of dx square is less than equal to, if I call, let's say if I call this as, let's say, alpha square, then it would be alpha square times 2 norm of x square. So from here we can say that dx divided by 2 norm of dx divided by norm x is less than equal to alpha, and this is true for all non-zero x, right? If this is true for all non-zero x, so clearly we can say from here that the 2 norm of, or the operator 2 norm of 2 of d is less than equal to alpha. Clearly we have found something. So we will show that, so from here we have found an upper bound. We have found one upper bound which is alpha, and we will show that this alpha is actually equality. So here we will show equality by showing that there exists a vector x for which this alpha is attained. That means for which this ratio is equal to alpha. Okay, so what I will do here, so I'm saying that this equality, here we have inequality, so thus equality holds if we show, so let me call this as 1, so it holds in 1 if we show that there exists a vector x, non-zero vector x in Cn such that uh, 2 norm of dx hat divided by 2 norm of x hat is, this ratio is equal to alpha. If this we show, then we can say that the 2 norm of d is actually equal to alpha. Now can you tell me which vector x hat I should choose here? So
Sir,
that yes.
if kth diagonal entry is maximum, then we choose a vector whose kth entry is 1 and all other entries are 0.
Yeah, so the vector is the kth standard vector. So let's say ek. So if let uh, k be such that alpha is equal to dk, so that means maximum over all these diagonal entries. So that maximum appears or occurs at the kth diagonal. Then you can choose x hat as ek. Ek is the kth standard unit vector in Cn, and this is just alpha. So this implies that the operator 2 norm of d is equal to alpha. But not only for this, in fact, if you want to show some other things also, like for other norms also, if you want to prove in the same way, then you have to follow the same procedure. You first first show that something is an upper bound, and then you show that that upper bound is uncertain. For example, uh, let us look at one more example here. So next we have, so far we have seen for only for diagonal matrices, but even if the matrix is not diagonal, there is a way that gives you two operator 2 norm of that matrix. For any given matrix, you can always tell what would be the operator 2 norm. That I will like state later on when we introduce like singular values. Okay, singular value decomposition. So the largest singular value actually gives you the, is equal to the 2 norm, operator 2 norm of a matrix. So for any given matrix A, if you find the largest singular value, then that gives you the that is actually equal to operator 2 norm of that matrix. But here I will not mention this. I will mention that later on, okay, when we introduce the singular value decomposition. But so far this is fine. But similarly, if suppose you want to find what would be the one norm, operator 1 norm of a matrix. So operator 1 norm of a matrix is nothing but, so what is the operator 1 norm by definition? It is just max over of the ratio 1 norm of ax divided by 1 norm of x. You can actually show that this is actually equal to the maximum column sum. So what I'm going to do next is the following. So I will show that, so the question is show that for any given matrix n, given matrix A of size n cross n over C, one norm, operator 1 norm is equal to the following. So what is this? It is the maximum column sum. So you do the following, and this index is varying, the summation is varying over I. So this is maximum column sum. You can see here, you what is this here? You take the so for example, when j equal to 1, you take the column sum of the sum of the first column, sum of the entries in the first column. Then when j equal to 2, you take the sum of the entries in the second column, and so on. You take all these sum and then take their maximum. This is what I'm calling as, this is what I'm going to show, that this is equal to operator 1 norm of A. Okay, so therefore this is also called as, so this is also called as maximum column sum norm. maximum column sum. Okay, because this operator one norm is equal to this one. Okay, so how to show this again? So let me call this as alpha. This is some quantity, right? It's a maximum. So this is just a scalar. This is the maximum over all column sum. So I'm calling this quantity as alpha. So I have to show that one norm of A, one norm of, operator one norm of A is equal to this alpha. That means the maximum of uh, this ratio is equal to alpha, right? This I have to show that this is equal to alpha. So if this is equal to alpha, I'll show that this is an upper bound, and then I'll show that this is the least upper bound by showing that this alpha is attained. Okay, so there are two-step process. I will first show that this alpha is an upper bound, and then I'll show that this is attained. Okay, so let us do that. Uh, so how to do this? So again, let me write what is one norm, operator one norm. It is the maximum of this ratio over all non-zero x. Right? Now, if I take any non-zero x, in Cn, and let us denote the entries of x as x1 to xn, then what would be the one norm of Ax? It is just by definition. This A is a matrix, so if I denote like let's say the entries of A by Aij, then what it would be? It would be this one, I equal to 1 to n, then summation here you take j equal to 1 to n, Aij xj, right? Because this is a matrix vector matrix vector product. So this is what we will have. So this is Ax. So when I equal to 1, this is the first entry. When I equal to 2, this would be the second. So you just take the summation of all these entries in of Ax. But then you can take this modulus inside. So because of triangle inequality, we will lose this equality here from equality here, and it becomes inequality. So I'll take this modulus inside. So it becomes this. Okay. Right. Now what I will do, I'll do the following. The same thing I can write in this way. So I'll take the summation with j outside and summation with I inside. Okay. So what I will do here, uh, I will do the following. I'll write it in this way. You can see that these two things are same. I'll just replace or the interchange the summation, but nothing is changed. It's the same thing. So now here you can see for each j, for a fixed j, this second term here, this is actually column sum, jth column sum, right? So if you replace this column sum with the maximum column sum, that means maximum over all the column sums, then and you call this as we are denoting it by alpha. So you can say that this is less than equal to alpha times j equal to 1 to n for xj. But then this is actually alpha times one norm of x. So what we can say is that ax, one norm of ax divided by one norm of x is less than equal to alpha for all non-zero x in Cn. So we have shown that this is an alpha is an upper bound for this. In order to say that this is attained, so what we want to show, we want to claim that this is equal to alpha. So for this, I will show again that this is attained. So can you again tell me which vector I should choose? Can you tell me which vector I should choose? So now we have to find a vector x hat such that the value of this ratio under one norm is equal to alpha. So can you tell me what x hat I should choose?
So vector with all entries 1 by n.
All entries by,
All entries which are equal to 1 by n.
but then will that give you required thing? That will not give you a vector. This vector would be of one norm, but it may not give you this alpha. So if suppose that, so you have maximum column sum, the same way you do like you did in the case of a diagonal matrix in the previous example. So suppose that the kth sum, kth column is the one which gives you the maximum sum. And then accordingly you choose your vector. So which vector? So see, if I want to, this is my matrix A, okay, which has n columns. If I want to extract the kth column, which vector I should multiply from right hand side so that I can get kth column of A?
Which kth entry is 1 and all other are 0.
Yeah, so it's like a kth unit vector. So if I do this A E K, then it gives me the the kth column of A. Now, if this is, I know that if the maximum is this is the column where the maximum column sum occurs, then I will just choose EK and that will do the job for me. So what I'm saying is that let K be such that this alpha, that means the maximum column sum occurs in the kth column. Okay. Then if I choose x hat as EK, that means the kth unit vector, then one norm of EK is just the kth. So what is this? AEK is the kth column, so it is just alpha equal to alpha. So this implies that one norm of A is equal to alpha. So now if now you know what would be the operator one norm of a matrix for any matrix. Here I have not assumed any particular matrix. I just said that A is any matrix of size n cross n, then its one norm is equal to, operator one norm is equal to maximum column sum. Similarly, you can show that for operator infinity norm, the operator infinity norm is equal to maximum row sum. So this you can use using by following exactly similar steps you can follow, and you can prove that. So you can prove that. So this I will give you as an exercise. You can prove that for any given matrix A of size n cross n, in operator infinity norm is actually equal to this one. This is maximum row sum. Right? I'll give you one more exercise and then I'll stop. Um, so far we have seen several norms or several matrix norms on space of matrices. I'll give you another way to or I'll give you one more way to define new matrix norms on a given matrix on matrix space. So how to do that? So this you can achieve by doing this exercise. So if suppose we have a norm, this is any matrix norm. So if this is a matrix norm on, let's say this space of matrices, and suppose that we have a matrix S, any matrix S which is invertible. Okay, so we are given a matrix now, and we are given a matrix S which is invertible. Then you can show that this new function which I'm defining by using this matrix S. So let's say, let us denote this function by this subscript S, just to mention that this is defined by using S. So how it is defined? If you if I denote this function by this, then how this function is defined? This is defined by, if you take any matrix A, then send it to the norm of S inverse AS. Okay, so then this function is a matrix norm on space of matrices. Okay, so for any given matrix norm and for any invertible matrix S, you can define actually a matrix norm on this. So this exercise gives you another way to define matrix norms on this. So this, why this is true, this you can verify quickly. This function, again, in order to check that this is a matrix norm, you have to check 5 properties. So the first 4 properties, they follow easily. This is not difficult to check. Why this is true? The first 4 properties, because here this is a norm. So using the norm properties of this, you can show that the first 4 properties are satisfied. Only thing is to check the submultiplicativity, but that is also true. So I'll give you some hint why that is true. Because if you take any 2 matrices A and B, then look at this function. By definition, it is just this one. But then you know that S is invertible, so I can write the same thing in this way. But then I can take this as one matrix and this as another matrix. So it would be less than equal to S inverse AS, S inverse BS, using the submultiplicativity of this given matrix norm, which is equal to S norm of A and product of S norm of A and S norm of B. All right. So this exercise gives you another way to define a matrix norm on a space of matrices. So with this, I will stop here, and I'll try to conclude this norm and matrix norm in the next class. So I'm sorry that I'm leaving you, or I'm stopping this class 30 minutes early. I promise that I'll take 30 minutes extra in the next class, maybe next class or next to next class. So whenever you will allow me to take 30 minutes extra, I will manage this 30 minutes in some other class. Okay. So if you have any doubt, you can ask. Otherwise, I will stop here. Okay. So if there is no doubt, then I'm
Sir, please
cutting off
send
now.
all lecture notes.
Yeah, so all the lecture notes are uploaded on MS Teams. So please check regularly after each lecture. I try to upload it the same day. But if not the same day, then the next morning I will do it for sure. But I'll try to do it on the same day. Okay.
Okay.
Okay, then see you on Monday. Bye.
Okay, sir. Thank you.
Thank you.